we're now going to move on to a new topic about prime numbers and prime factorizations. First thing we're going to do is talk about what a prime factorization of a natural number is, at least in broad strokes. It won't be until the end of the video that we'll actually get a precise definition. We're going to define what prime numbers are, and then we're going to state the fundamental theorem of arithmetic. All right, so here's a definition. And warning, some of the definitions in this one are not going to be precise. So suppose n is a natural number. A factorization of n is an expression of n as a product of other natural numbers. Now this one's precise. For instance, if I take 12 and write it as 4 times 3, that is an example of a factorization of 12. So here's a not precise definition coming up. A prime factorization of n is a factorization of n into numbers that cannot be significantly factored any further. And of course, when I say cannot be significantly factored any further, that is not a very precise statement. That's the part we're going to have to hone in on and try to make a little more clear. And for another not precise definition, a prime number is a number that itself cannot be significantly factored any further. And again, significantly factored any further, we have to say what that means. So we have 12 is equal to 4 times 3. That is a factorization. But it turns out it's not a prime factorization because 4 is equal to 2 times 2. And as we will see later, we will consider that a significant factorization. It can be factored further. But then that also means that 12 is not a prime number because we can factor it into a significant factorization as well. 4 times 3 is significant, and so 12 is not a prime number. And again, what makes it significant? That's a fair question. So we'll get to that, I promise. Oh, that's good. We're answering the question right here. What do we mean by cannot be significantly factored any further? Well, let's see. Let's try some things and see if we think they can be significant factorizations. So here's the number 3, which I'm going to factor into 3 times 1, and that's a perfectly valid factorization. Factorization just means you multiply two numbers together to get the number. 3 times 1 is 3. That's a factorization. So is that significant factorization? Well, let's see. There are 2 possible answers to that question, right? Either yes or no. And let's consider each one individually. So if the answer is yes, right, that means that literally every natural number can be significantly factored, right? So if I have a number n, I can factor it into n times 1. That's a significant factoring, and that's not great because that says every natural number can be significantly factored. That means there are no primes anywhere. Yeah, we don't want that. We don't want that. All right. So the answer is no. Well, if the answer is no, here's another uncomfortable conclusion that we have to draw. 1 then cannot be a prime number. All right? Because if it is a prime number, then we can factor into 1 equals 1 times 1. And if 1's a prime number, then 1 times 1 is a significant factoring, right? So, so 1 can't be a prime number. So that is going to deeply affect our definition of prime number. So here's what we have. A prime number is a natural number p such that a couple things happen. First of all, since we want to exclude 1 for the reasons that we've already discussed, that p has to be greater than or equal to 2. And then the only divisors of p are 1 and p, because if we get anything else, then we get a significant factorization of p. And then a prime factorization of a natural number n is a factorization of n into prime numbers. So here are some important questions that we're going to ask. Which natural numbers are there that have a prime factorization? If you have a natural number, how many prime factorizations can it have? Can it have more than 1? And actually, a question we should ask before that one maybe is, if we did have 2 prime factorizations, what would it mean for them to be different? That sounds a little silly, but it turns out to be a little bit more subtle than it sounds. And we're going to answer all those questions in the following theorem that is called the fundamental theorem of arithmetic. So here's how this one goes. Every integer that is at least 2 is prime or has a prime factorization. That's the first part of it. That's actually what we call the existence part of the fundamental theorem of arithmetic. Every integer that is at least 2, a prime factorization exists. But then, the prime factorization is unique up to the order of the primes the factorization are written. In other words, if we take a prime factorization and just write the same prime factorization by writing the primes in a different order, we don't count that as different. All right, so now I think you are ready to work on the next set of activities. That is the fundamental theorem of arithmetic existence, and that is the PDF file included with this video.